Welcome back to this Forge College Explainer. So, if you survived the grueling trenches of our previous lesson on debugging and optimizing interaction processes, honestly, give yourself a massive pat on the back. You've officially made it to the capstone of our Programming with Solana track. Today, we're literally putting everything together. We're going to take all those individual parts we've been painstakingly crafting and assemble them into a masterful, fully functional client interaction machine. Let's get right into it.
Now, I'm guessing right now, your workspace probably looks a bit like a metaphorical messy garage, right? We've got project plans, interface definitions, optimized components, deployment scripts, just kind of lying around everywhere. It's a scattered pile of code. But today, the whole goal is to turn those loose screws and solitary gears into one cohesive deployable Solana client script. We're officially shifting gears from just building parts to final assembly.
Here's our schematic overview for today. First, the grand capstone blueprint. Then, defining what done means. After that, wiring the assembly line, hitting our quality assurance checkpoint, and finally, shipping the final build.
All right, Section 1, the grand capstone blueprint, where we quickly recap our technical artifacts. Because, we really can't build the machine if we don't know what parts we actually have in our inventory.
So our mission here is to take all those scattered artifacts, your project plans, the interface specs, the deploy scripts, and synthesize them into a beautifully humming engine, the unified Capstone client binary. No more separate, disjointed exercises. This is the grand unification we've been waiting for.
Moving on to Section 2, defining what done means, going over the milestone acceptance criteria. Before we start bolting things down and just crossing our fingers, we need to consult the spec sheet.
Because in engineering, done doesn't just mean, well, it didn't crash on my machine. To pass final inspection, our machine has to hit 5 core criteria. First up, an executable script, meaning it actually has to build without warnings on stable Rust. Second is transaction correctness. It must execute our planned complex flows flawlessly. Third, we need a reproducible deployment recipe so anyone else can spin it up and get the exact same results. Fourth, robust error handling. Handling those super annoying transient RPC errors with that sweet backoff strategy we perfected earlier. And finally, integration fidelity, meaning the behaviors perfectly match our interface definitions.
Okay, Section 3, wiring the assembly line, building the Rust implementation. With our standards set, it's finally time to build.
The real magic happens right in our main .rs orchestrator, where all those disparate modules finally talk to each other. The assembly line follows 3 strict logical steps here. Step 1, we read the configuration which acts as the brain, pulling straight from our interface spec. Step 2, the hands of the machine build and sign the instruction payloads using those exact serializers we validated previously. And Step 3, we pass that payload to the optimized transaction processor. Yep, the exact same one we rigorously debugged in our last lesson. It is a beautifully clean pipeline.
But hey, we don't want a machine that only does one thing and can't be controlled, right? We need a steering wheel. So we're going to wire up a command line interface, a CLI runner. By using simple flags like --flow create account or --flow full run, we give ourselves the power to easily test single components or just fire up the entire engine all at once. This makes testing and actually operating the script infinitely easier.
That brings us to Section 4, our quality assurance checkpoint, running the diagnostics. Now that our gears are wired up, we have to ensure this engine actually purrs and doesn't just sputter, stall out, or, catch fire on the starting line.
Our validation follows 3 exact steps. Step 1 is the build, running cargo build -- release and expecting the binary to complete without panicking. Step 2 is deploy, executing our reproducible deployment recipe with /deploy.sh to automatically set up the environment. And Step 3 is test, running cargo tests to make sure our end-to-end integration passes perfectly. If all 3 of these steps succeed, you've got a seriously solid working foundation.
But listen, we can't just test for sunny days, right? We have to test for storms. We also need to run a stress test by simulating a transient RPC failure. Basically, this means we intentionally throttle an endpoint or temporarily block network access. Now, why on earth would we be so cruel to our own code? Well, because we need to absolutely verify that our error handling and retry strategies kick in properly, instead of just letting the whole machine crash and burn at the very first sign of network trouble.
Finally, Section 5, shipping the final build, packaging and key principles.
Assuming our machine survived that stress test, we need to box up our creation. A truly great engineer ensures someone else can reproduce their exact runtime environment using the provided artifacts. So what actually goes into your shipping crate?
Think of these as your stretch packaging goals to really make your evaluators smile. Number 1, a small release artifact, like a tarball containing your compiled binary and configuration. Number 2, an automated validate.sh script that runs your primary end-to-end flow and reports a crystal clear pass or fail. And number 3, a beautifully documented checkpoint report detailing your logs and test outputs.
If there is one absolutely crucial point to remember as a master engineer wrapping up this capstone, it's this. Treat your interface_spec.yaml as the absolute source of truth. Seriously. If you wire your code strictly to this contract, you are going to drastically minimize those headache-inducing serialization mismatches that plague lesser developers. It's a total game changer.
Just look at what you've accomplished here. You have successfully built a reproducible, verified, incredibly robust client script. But, as with all things in Web3, the rabbit hole always goes deeper. You've mastered interacting with a single setup, but the next logical question is, how do we extend this beautiful orchestrator to coordinate complex transactions across multiple on-chain programs at the exact same time?
Well, that highly anticipated question will be answered in our next lesson on the fundamentals of cross-program invocations. But for now, please take a moment to celebrate assembling your Capstone script. You earned it. Thank you so much for joining this Forge College Explainer. To dive deeper into this subject and explore a massive library of other fascinating Web3 topics, head on over to our website at forge.college. Happy coding, and we'll see you in the next one.